Gnanam paramam dheyam. Knowledge is supreme.
Okay, so I am going to bring you to this notation of Dirac, introduced it in 1920s, a notation which is some kind of an angular bracket. It's called bracket notation, which we are going to follow. Okay. State of a quantum mechanical system is denoted by this kind of a angular bracket, which is called Dirac. Okay, so let me try to introduce this for you. So, state of quantum mechanical system we denote this by an angular bracket with a Greek letter psi, can be psi, phi. This is a kind of notation which we are going to use. And in principle, the state of the system contains all the information about the system, and it can be evolving as a function of time. Okay. The state is denoted, this psi is an element of some vector space V. Okay, so this is the notation which we are going to use, not the vector A, vector B and so on. We are going to use an abstract notation which is an angular bracket, and this angular bracket is known as ket. So you can write again in this notation, suppose the vector space, if you have psi, phi, I will suppress the time right now, chi, dot dot dot, which are elements of a vector space, then what do you have to do? You have to satisfy those familiar properties which we were studying. What are those properties? Psi plus phi should be an element of V. What else? Psi plus phi plus chi. You can also satisfy this associativity property, same as psi plus phi plus chi. Exactly like what we did for the vectors in R3, but there could be a long list here. This is a long list which I have for an abstract vector space. I don't know what is the dimensionality of this vector space. I don't know the linear independent, the set which spans the space. Now I am putting it in this abstract notation. Is that clear? I really don't know what they are, and our aim is to fix all these things. Given a quantum mechanical system, what is the basis set? How to write the states in terms of the basis set? And also we need to give a prescription or an equation to determine, just like in Newton's law. All this Newton's law, what does it tell us? It tells you the trajectory of the particle x as a function of t, right? You get position of a particle in Newton's law as a function of t, solving those equations. X as a function of t you will not be able to get unless you give a set of equations. Similarly, I need to give an equation, an empirical equation, to solve this, to find the time evolution of the state. And before even we go into it, is this vector space a linear vector space? If this is a linear vector space, then these properties have to be satisfied. If these properties are not satisfied, then it's not even a linear vector space. So these are things which we need to know, and whatever is psi has all the information about the system. Okay. So this is an abstract notation, slightly different from your wave functions. We'll come back to the wave function later. Right now, let's take that the state of a system is encoded in this angular bracket state, which is called as a ket vector, which can evolve in time. There is a prescription equation, which is the Schrodinger equation actually, but how it is written in this Dirac notation we need to see, and we need to satisfy all these properties. So this also could be commutative, right? The combination of adding two states in a vector space, you can interchange the order, it will be again an element of this vector space, it will satisfy this associativity property. So in fact this set, if it satisfies this property, you call it as a linear vector space. Okay. So then we say that this is a linear vector space if it satisfies these properties in the language of this angular notation. So how do we define? So there is also the scalar multiplying, which I didn't write, but you can put it in. So if you have a scalar on psi, this is also an element of the vector space, and you will have A and then you have a B on psi. This will be AB multiplying on psi. This is also true. This also I wrote last time on the R3 vector space. If you have something like this, you can do the distributive, right, something like this, sorry, A on psi plus A on phi. These are things which you do it on a vector space, you can do this here also. If psi adds to something and gives you psi, what do we call this state? Doesn't do anything to the state. In your R3, it is like a vector with components 0, 0, 0. It's called as a null vector. What is the null vector? Null vector is one whose components are all 0, or the length of the null vector will be, norm of the null vector will be 0, right. So if you add a null vector to psi, you get back the same state. A null vector will have norm to be 0, but how do you find the norm? That brings us to the concept of, you need to find a dot product. But in any abstract linear vector space, you have a dual vector space V tilde, which could be different from V. Most of the situations V tilde may look similar to V. In fact, in R3, you take vectors and take a dot product because V tilde is exactly similar to V. Okay. But in general, a dual vector space will be different from your original vector space, where we denote states by a different angular bracket. This is called bra. Okay. Dirac introduced this notation, we all universally follow it. So this is the one which is the angular bracket, which is written in the opposite fashion. So, this bra notation which we introduce, this will also satisfy the same set of properties which you saw for the vector space V, but in this notation. So, you will have psi plus phi should be an element of V tilde and so on. So, why have we introduced this notation? So, with this notation we can define an inner product, so the quote unquote dot product which we studied in R3. We could write some psi times phi, a ket contracted with the bra. This is supposed to be like a dot product which will give you a scalar, and this is sometimes called as a inner product. Okay. So, to make contact with your familiar R3, let us do this. Let us write the ket vector as a column. Okay, suppose I want to write a ket vector psi as x1, x2 and x3. Then to get a number, you are all familiar with Mattox Mechanics. The corresponding dual vector will be denoted by x1, x2, x3. These are elements of R3, that means real entries. The corresponding dual vector is a row. We have all done this many times. So, this is a row or it is a transpose of this in real vector space. R3 is a real vector space because the entries are all real, and you know that what is the length of the vector when I ask, which is square root of this, which we denoted by psi. That is just your x1 squared plus x2 squared plus x3 squared. They are sum of squares, should be positive. This norm of the vector psi should always be positive, and it should also be finite. It should be finite, right? It should not be infinity. Norm of the length of the vector cannot be infinity. It should be positive and finite. These restrictions we can see in R3. Whenever we take vectors, we make sure that you do not take vectors with length infinity. You work with finite vectors, and the 0 vector is with 0 components, x1, x2, x3 are all 0, and you get the length of this vector. Right? Suppose instead of R3, I want to go to a complex vector space. Like we have done complex plane. Complex plane has one z coordinate, but I could look at two z coordinate in an abstract complex vector space. If you do such things, suppose x1 is complex, x2 is complex, x3 is complex. Suppose if I take the inner product, what will happen to this? It will become complex, right? If x1, x2, x3 are complex, x1 squared plus x2 squared plus x3 squared, x1 squared will be complex, x2 squared will be complex, x3. But then this meaning of calling it as a length of a vector loses its meaning. You do not want a complex quantity for a length of a vector. What is the better option? Which you do mechanically in matrix mechanics. Matrices, what do? You don't only transpose, general matrices have entries which are complex conjugate and transpose, which is what is called as an adjoint operation. So this is also like a matrix, it's not a square matrix. So when I go to this dual space, in principle I should take the complex conjugate, correct? If I do that, then this one will be mod x1 squared, mod x2 squared and mod x3 squared. Then this will be positive. So in an abstract vector space, if I take a vector defined by, at least for the finite dimensional, so this will give you the number of components here, tells you that any arbitrary state, what is the dimension of the space. So suppose I take it to be 3 dimension, and I can take the abstract state as written in terms of these components in a column vector. The dual vector, which is denoted by this angular bracket, so this one is called ket, this one is called bra. The corresponding dual vector should be written interchanging the column to a row and also complex conjugating the coefficients, so that the inner product, which you are all defined so far, for the specific vector and its dual vector, this one and this one, that will be positive definite if we define the ket as a column and the bra as a row with complex conjugation. Now my next question is, this psi with phi, what is the property psi with phi satisfies? Psi with phi is like an inner product of two different vectors. Okay, you have a vector psi, you have another vector phi, and it is a dot product of two different vectors. What happens? Does that remain same if you interchange, if you put phi to be in the dual vector space and psi to be in the vector space? So what is the property it satisfies? Psi phi question mark, phi psi, no. So suppose I take psi to be, let's say A1, A2, A3, which are complex, and we take phi to be B1, B2, B3, which are complex. What is psi phi? Which is A1 star B1 plus A2 star B2 plus A3 star B3. What is phi with psi? B1 star A1 plus B2 star A2. Okay. So what do we see from this? Psi phi is phi psi. You take the inner product and complex conjugate it. The complex conjugate of this will give me this, right? This ordering is unimportant. Calling it as B1 star A1 is same as A1 B1 star. The star of that is same as this one. So this is a property in a general complex vector space. If it is real, left hand side is real, right hand side is real, complex conjugation is not required. but in general the vector space could have complex entries, and you need to make sure that the inner product of any two vectors will be, if you interchange the dual vector and the vector, it will be a complex one. So please get used to this notation. So that's why I am spending some time so that you are familiar with this notation, and then you will see how powerful this notation is. Okay, here is kind of a block summary of what I said right now, which is the Dirac bracket notation. State of a quantum mechanical system is denoted by an angular bracket, which was called by Dirac as ket, and they are vectors in a abstract linear vector space. Even though I am trying to map it to a known 3-dimensional vector space, you can do it for, in general, an abstract vector space, whatever I said, as long as you follow the axioms. Is that clear? I did this specifically with R3 in mind so that you understand, but you can do it for any n-dimensional vector space where n could be very, very large also. A dual vector space are denoted by another angular bracket which is called as bra, and then the dot product. You need the dual vector space, otherwise you can't define this inner product. So the inner product is the one which will give you the length and other scalars. The immediate question which you all know, when you sum up two vectors in the triangle, if A, B and C are the norms of vectors A, B and C which denotes the sides of a triangle, what are the properties it should satisfy? Sum of two sides should be greater than or less than, sum of two sides should be greater than or equal to the third side. So these are things which you all know, and we need to prove this in the Dirac bracket notation. Okay. So let's try and prove this. Incidentally, a couple of questions for you. If you have a set of matrices given, does that form a vector space? Let's take set of 2 by 2 matrices. Do they form a vector space? Yes. You can add two matrices to get another matrix which is also a 2 by 2 matrix. So it forms a vector space. So there are various examples. You can take a set of real numbers. They also form a vector space. Set of complex numbers, they also form a vector space. You can also have column vectors with a column with n entries, they form an n-dimensional vector space, and so on. So you can have examples. You can also have examples where you can take a differential equation and find a solution. There can be many solutions to the differential equation, and the linear combinations of the solution will also be a solution of this differential equation, like Schrodinger equation which you have seen. Stationary states are solutions. Linear combinations of the stationary states are also solutions. You can start doing this. So they also form a vector space. All the stationary states set also forms a vector space. So there are various examples you can do.